because I've understood there's a program after this for me as well. So let's get the last lecture of today about the fabrication by replication. Let's get that out of the way. So I hope you all enjoyed a nice lunch and be able to change your mind a little bit, because as we were just talking, doing a whole list of lectures. How can I just stop the standard transitions? I need to look at that tonight. So it's always good to change your mind and be able to then refocus on the subject, because I realize I send a lot of information your way and it becomes really hard to give it all a little bit of a place in your brain. So as a summary, this morning we started off talking about microfabrication and then learned that photolithography is the heart of any microfabrication. How do you like my new laser pointer? It is a pointer, and it also a little flower and can do multiple colors. So if it gets really boring, I'll just put that up and you can watch that one. So we started off about photolithography, where we used a mask with opaque and transparent areas to selectively illuminate a photosensitive layer that we coated onto a flat substrate. Based on photochemistry, this interaction of the light with the light-sensitive material made this material change its properties, and then it became either soluble or insoluble in the developer solution, which means that we could selectively remove the exposed or the non-exposed areas, and that way we could leave little tracks on the wafer in the photoresist that we could then either use as a template for soft lithography, or we could, when this photoresist was removed, use it as an etching mask for wet etching in glass. We built on that knowledge to talk about soft lithography, which is the casting of PDMS, an elastomer, over a template. And then PDMS is very good at replicating any surface features down to the nanometer scale. PDMS, you buy it as a 2-component mixture. You mix it in around a 1:10 ratio. The small bottle is a thermocatalyst that makes sure that the PDMS polymerizes when it's heated up. And typically you do the baking of the PDMS in the oven at a temperature anywhere between 55 degrees and 80 degrees. So you want to have it so hot that your cooking time is relatively short, about an hour or two. But you also want to prevent that any of your plastics that you use, either the Petri dish or maybe your template was 3D printed in a thermoplastic. So you want to prevent any of your materials from melting. You don't want any of your water that could be present to be boiling off. So you want to be at moderate temperature. But as anything in reaction kinetics, the warmer it is, the faster it goes. So you've got shorter cooking times or shorter times in the oven if you move up towards the 80 degrees. Whereas if for any reason you need to do your curing of PDMS at 55, you need to wait a little bit longer. So it's about an hour at 80 degrees, probably 3-4 hours when you do the cooking at 55 degrees. It's not very hard to identify that you didn't cook it long enough, because if you're making a cake, how do you know your cake isn't done yet? Fork. And what happens if the cake is not done?
So the liquid metal will stick to the fork and you'll come to know.
Yeah.
It's not good.
Exactly the same thing with PDMS. If the PDMS is not good, it's still sticky. It's still the sticky liquid. And you've seen all the precautions in the lab, using aluminium foil everywhere and having wipes nearby. It is very, very sticky, and there's no solvent that removes it. So you'll be there with a razor blade scraping it off the table if you do spill it. If it's not cured yet, you still have got your sticky goo that will literally stick to everything, to your gloves, to your door handles, to your tabletop, to your pen, to your balance. Everything will and it stays sticky for weeks. So if you think it's still sticky, leave it for another hour. It is very hard to overcure it, so it won't get dry like a cake. But you don't want your PDMS to be sticky, because then you'll have sticky stuff for weeks and weeks in your laboratory. What we'll be talking about during this lecture is mainly about injection molding, which is a large industrial scale process for making lots and lots of different devices. And these devices are made in plastics. And I'm not sure who's done any polymer chemistry here. Do you know the difference in plastic between a thermoset and a thermoplastic?
Thermoplastics can be remolded once heated, whereas thermosets cannot.
Yeah. So if you heat a thermoset up, at a certain point it burns, but it will never melt and start dripping. Whereas a thermoplastic, if you heat it up to around its softening point, it becomes flowy and fluid again. So that is exactly the property that we use to replicate our devices with high speed. So for injection molding, you want to use thermoplastics. And there's a couple of different ways of molding. Injection molding, as I just said, is the most frequently used techniques. But there's also hot embossing and compression molding. All three have in common that they use a thermoplastic. They heat a thermoplastic up to the temperature that it becomes a viscous liquid. That allows it to shape the liquid to the geometries that you want to replicate in a cavity. Then the temperature is dropped. If for a thermoplastic the temperature decreases, the plastic turns again from being in its liquid state to be in its solid state, and we have a solid device or a bit of plastic being formed. So in injection molding, the name is already much saying, you inject the thermoplastic into the mold. This means that we can get high throughput of hundreds is even conservative, thousands per mold you can make. And we have a number of different, in my research group we recently purchased a 2-component injection molder where we have a PDMS base and a curing agent that are mixed together and then molded into the hot cavity to then do a very quick bake, as we just spoke about the PDMS, and then the injection molded device comes out. So there is technology developing to do injection molding in 2-component mixture as well for then the thermoset polymers, but the vast majority is thermoplastics. Same thing for hot embossing, but the process works slightly different. We don't have the plastic heated up to the point that it's flowy, we just make it soft. And then we push a stamp like a cookie cutter into the soft material, we allow it to cool down, that it's solid, we remove the stamp, and we've got the structures stamped in. So in injection molding, we really are pumping liquid polymer into the cavities. With hot embossing, it comes to just above the softening point, and we squash a template into the soft polymer. And then there's compression molding where we've got a film and the film is shaped around the parts. Here we've got an image of the injection molder that I've got in my research group. So I've got a fantastic engineer in my group, Richard Alexander. A lot of the manufacturing parts here are all done by his hands. So he did an undergraduate and a PhD in mechanical engineering and has perfected how to engineer for manufacturing of microfluidics. And we are fairly unique at where we are. Mostly research groups don't have industrial instrumentation, but we've got a large-scale injection molder. Like, if we start at the start of the stage there, the injection molder would come to here. It is a large bit of equipment, like they use to make drink bottles, plastic cups. So what happens in the injection molder is that we've got a feeder hopper, and you put a pelletized polymer in there. Could be any thermopolymer. The injection molder provides with control that you can adjust the temperatures, and therefore we can do PMMA, COC, that they are the main interest. Polystyrene, they're the main polymers that are of interest for microfluidics because those polymers are transparent. Not to as deep a UV light as PDMS, but certainly COC is coming with reasonable transparency at 380 nanometers and up. PMMA is a little bit higher. PMMA cuts out at around 450, 460 nanometers. So really the low 400 nanometer detection you can't do anymore. You need to go to the higher wavelengths. But the material comes in as little pellets, about half a centimeter, granular material. It sits in the hopper, it's getting a little bit of nitrogen being purged through to make sure it's dry and there's no water in there. Because if there's water and it gets heated up, it gets steam and all kinds of things. Then it's fed here into the screw. And this screw is rotated slowly so that the pellets are entering. And here you can see that there's heat, so this temperature moves up. So we get the screw mechanically, like industrial diggers work, where you can dig a core. The polymer is being moved forward through the rotation of this screw into a warmer and warmer environment, which means that it gets increasingly liquid. So we start off with pellets here. Here we probably have got a gooey mass, and here we've got a reasonably thin liquid. This liquid then, under the pressure of this screw that is pushing more and more material forward, the plastic comes out of a nozzle with high pressure and is injected, squirted into a cavity. We can see the cavity here has got some open spaces, and that is where we will be making our microfluidic devices in this instance. Works the same thing for phone covers, but we do microfluidics here. So this mold, you can see the arrows here, is sitting in place. We've got a small cavity. The screw pushes the polymer into the cavity. It fills. It cools down. The cooled down part drops down into the supply basket after this platen is removed back anymore. So it comes back. This is all heated up to the melting point of the polymer. The liquid polymer is injected into the warm cavity where it stays a liquid and fills all the nooks and crannies. There's little holes there to vacate any air if that would be still present there. Then this is cooled down so that the polymer gets back to its solid state. The platen moves to the back and the device drops in the basket. And here on the movie you can see how that takes place. So you can see the platen pushes the device away, cavity closes, liquid polymer is being injected. We then get cooling down. And then if the movie still plays, and comes out. Moves, part is being injected, comes out, and the push pins push it out. So this is happening real time. So every 5 or so seconds, we have a new freshly baked chip falling into a basket. And that is unprecedented. There's no other microfabrication techniques that go this fast. Problem, however, it is really expensive to make this part. So we can make many devices, thousands with one mold, but it costs tens of thousands of dollars. So multiply by 50, so $500,000 rupees or so to make the template to start making your first device. So injection molding is very attractive if you are ready to commercialize and you want to make 5,000, 10,000 different devices because you want to start selling them. Then it's not a problem to have high startup cost because your cost per device will be really low. If you're a PhD student with very little funding trying to do some microfabrication, injection molding is perhaps not what you want to do because you'll spend a lot of money making the mold and you'll only use 4 or 5 devices. So good for scaling, good for making lots of devices, depending on what your research project is. If you're relatively early in testing out the methodology, making an injection moldable device is probably not for you. So it's the top end, it's the Mercedes of large-scale manufacturing. Hot embossing is a little bit less expensive because the mold is not under as much pressure as the cavity and injection molding. You need to have very strong materials, high grade levels of stainless steel or aluminium being milled because your liquid polymer in injection molding is injected under high pressure. So you need to make sure that nothing moves or changes. Whereas in hot embossing is a little bit more gentle. We start off with the template or the inverse of the structure that we want to have on the top, and we've got a polymer here on the bottom. We warm both of them up to the softening point of the polymer. So both the template is warm and the polymer is warm. We then push the template into the polymer, which is soft. So the polymer will deform where the ridges here are sticking out, and this polymer will displace. We then can cool down the mold, and the polymer with that cools down slowly as well, after which we can release the template, and we have our polymer device on one hand and our template on the other hand, and we can move again back to A, have our template, have a fresh bit of plastic, warm it up, imprint it, cool it down, and have the next one. Now that's why the techniques that we're now talking about are replication techniques. We go over and over again in the same loop, and with hot embossing we can make 50, 60, 80, if you're lucky 100 devices, so it's reasonable scale. It's a lot better than PDMS. If you use a photoresist template, somewhere between 10 and 15 bits start breaking off. So you can do a lot more with hot embossing than you can do with soft lithography, but is nowhere near at the throughput scale of injection molding. Compression molding sits kind of in the middle, but again we have a template here where we have a bit of polymer, so we load the polymer into our device. This is a moving part, this is a fixed part. With compression molding we apply more pressure than with injection molding, and you can see here that there's only a thin shim being left with compression molding, so you don't make large chunks of plastic. We then cool down again. This ejector pin can push the device out of the cavity once it's open again. Then we can load a new charge or a new bit of plastic, and the same thing happens again. So compression molding, very, very similar to hot embossing. There's also soft embossing, which is an approach where you use PDMS and not a hard mold to do hot embossing. So the hot embossing that I just showed was made with metal formed templates made using the Liga process, where you first do fine machining using photolithography. Then you electrochemically deposit a metal, typically nickel, on top. And that then becomes your hot embossing material to replicate your devices. So you're talking with a really strong metal mold. PDMS can be used as well if you control your processing parameters a little bit. So PDMS is a thermal insulator, so you need to heat it for a little bit longer. But it has been used very effectively to shape complex features into a thermoplastic. And after this has been pushed together, cooled down, the polymer is a solid again. The great advantage of PDMS is that you can easily peel it out because it deforms if you put pressure on it, which means that these complex, intricate structures are very easy to demold when you use soft embossing. If you use injection molding, you may need certain tapered sides in order to demold effectively, because you don't want to break off half your delicate microfluidic structure by removing your substrate. Here we've got a device where we first photolithographically pattern a resin, and then casting and curing that polymer, which then can be placed in contact with a PMMA plate. So we first use light and a mask to photolithography make a template. after development, casting and curing, you can replicate this from a positive in a negative in PDMS, and then we can use that PDMS to put it in contact with a PMMA plate. You can then do kind of an in-house injection molding by using paper clamps to apply equal pressure across your device, put it in the oven to warm it up, demold, and you've got your PMMA device. So as you'll see throughout today, hot embossing, this is the standard process. It requires an expensive instrument. If you understand what the process does and you just need to get a polymer to flow to around the softening point to imprint a fluidic structure, you can actually do it using a low budget approach as well, and quite well. So here we can see some images on how these channels after hot embossing using the paperclip method actually works. So we've got different exposure times here. Here we've got the original negative, then the PDMS replicate, which becomes the positive, and then this PDMS positive is replicated into PMMA. So photolithography made in reverse into PDMS, then imprinted into PMMA. And you can see the structure is really nicely replicated from one feature to another. One is negative, the other one is positive, but we get very good replication of our features that were present after photolithography on our template, cast from a positive into a negative, and then replicated into a microchannel. So this is the way that the channels look like, and in this instance it is nicely sealed. But if we think closely about the engineering challenges in injection molding, you've seen the movie coming in and out, and you can see that the device that is printed is released very easily from the mold. And that is because every part that you make by injection molding doesn't have vertical side walls. Because if it would have vertical side walls, it would be near impossible to slide it out of the mold again, because it would suck itself into place. So all the designs that we do, they don't have square sides as we tend to easily draw. They always need to have a draft angle, which is here to the side. One of the problems of a draft angle is that actually optical detection from the side becomes really difficult.
Can you repeat the draft angle?
So with the injection molding, we squeeze the material into a cavity, and we then want to be able to push it out again. If that goes with vertical walls, it requires a lot of force and it will be very difficult to get it out. Whereas if we have a small angle, then once we've got a little bit of movement, our whole device becomes loose and it's a lot easier to get out. Again, unlike cooking as an example, if you make a cake and you look at your mold to make a cake, it doesn't have right angles, it's got a little angle. And that is the draft angle, and that means that once you've made your cake and you want to get it out of the mold, the draft angle helps in that process. Microfabrication is just like making cakes. So same angle, same engineering concept, it's easier to get something out of that doesn't have perfectly straight walls. So for a research project where we wanted to do fluorescence detection coming from the sides, this draft angle, this having a non-vertical side, actually becomes really difficult because you get it to work like a mirror. If your light shines to an angled surface, it will get reflected. So we developed a way that we could create a little detection window with a perfectly vertical side wall by making some changes to our mold. And what Richard figured out there is having a little insert, it was part of the mold, that had a draft angle, except for the little part that reflected the thickness of our microfluidic device. This element was put inside the injection mold, inside the mold, but then was spring-loaded. So when we were pushing our device out of the machine, this could move along with the device, and then by the time it could fold out to the side, that would be happening. So this is in here, we have in the lab, we've got a CNC machine which mills really quickly with a spinning head, and we can go down to about 50 micron geometries. So we made this aluminium template by CNC milling, where this in here is the base, and this reservoir here is 50 micron high. So here 50 micron high features. You can see some different reaction chambers because we want to do lysis DNA extraction amplification in these devices with fluorescent detection of the end product. So by having a special part in the mold that could leave the device earlier because it had the draft angles, except for the little height of our device, with the pushing out, this device could move along, but then as soon as our device, polymer device fell out of the machine, the springs would pull it back in place, and once the plate is closed again, it was there to make the next device. And here you can see through the side of the device, you can see now very nicely the geometries of the microchannels where we could do sensitive fluorescence detection. A more recent project that I thought would be nice to get your head around again, what is all this microfluidic stuff good for? We are working together with Reza, and Reza is from Monash University, and Reza works on fertility, and in particular on in this project on how can we select the best swimming sperm. So he's developed a microfluidic device with a whole range of small microchannels, with the idea if sperm is motile, it will find a way to swim from one side of the microchannel to the other. Whereas if it's not motile, it won't be able to find the entrance nor the exit. So in this device, we load the semen to the outside. The good swimmers will be able to find themselves a way to the inside, whereas the not so competent swimmers will just stay outside and go to the waste. This means that you can select the best swimming sperm cells for in vitro fertilization from the central well. So Reza has developed this initially with soft lithography, has then made some changes to make it more complex using 3D printing. He's now got the problem or the luxury that he's working with the large in vitro fertilization agents, and he needs thousands of devices, which means that he can no longer make them by 3D printing because that's not as scalable financially. And we now need to translate the design that was made by 3D printing to make it good for injection molding, so we can make thousands of these devices for him, and we can start testing in human IVF clinics as well as for animal breeding. So there's a lot of interest in this kind of technology for cattle breeding as well. And horse breeding, there's a lot of money in that as well, clearly. So I've been talking a little bit between the lines about scalability and cost. And we recently wrote a book chapter where we actually did the numbers for a microfluidic device that by the time that you get your slides, you see a little bit bigger picture. Doesn't really show up well, but we've got a microfluidic device that got microchannels on both sides. So both the bottom side and the top side have got some fluidics. We've got a sample inlet sitting here at the back that distributes our sample through different channels on the bottom. Then we've got some mixing happening with reagents when it's getting back. And then the sample there from the different channels ends up in the cuvettes, where the height of the cuvette becomes the detection path length for photometric detection. We looked at the cost per device that this would be in dollars, from $100 to $500, if we would make these devices by 3D printing or by injection molding. So 3D printing we'll be learning more about later this week. But there are, you can ask a printing company to print paper. There's also companies that will 3D print. So you send your design to the company, you wait 2 or 3 days, and then the box comes to your place with a 3D printing company. So they have the expensive machines, and they sell you for very reasonable cost. They sell you the prints. So we got this design into their calculator, and we calculated that the device like this would be around $125 to make. And it didn't matter if we made 10, 1,000, 3,000 or 5,000. The cost per device was exactly the same. There is no benefit of scaling in 3D printing because the amount of labor per device is exactly the same. We can't increase the throughput. So we've got a flat line. But then with injection molding, I already said that the startup price is really high because we need to make the molds. But once we've got the mold, really our only cost is a couple of cents for the plastic. So you can see that the more devices you make, the cheaper injection molding becomes. And around 1,500 devices for this particular design is the break-even point where there is no difference between 3D printing and injection molding. So for this rather complex design, unless you need 1,500 devices, there is no need for injection molding. 3D printing will be as easy and convenient. And if you want to make some changes to design, you're not locked in. If you want to go commercial, you want to go thousands of devices, by all means, injection molding will be your friend because the more you make, the cheaper it gets. Because this line will be continuing to be horizontal. This one will be getting closer and closer to a couple of cents. If we look a little bit closer at how the cost structure for injection molding works, we have the time that it takes to set up the machine and the method, and that will not be changing. That's a base cost. Then we've got the price to make a mold. For very few devices, that's a couple of $1,000. But there is a scaling factor where you want to go to a better quality mold so you can do more devices. So the orange becomes higher. And then we've got the materials cost and assembly. Materials scales linear assembly as well. So you can see that there's a couple of points that all of a sudden you've got a step change in your manufacturing chain, and that is when the end of the lifetime of your mold comes. It's the same like your car. If you're driving your car, it normally costs kind of the standard money that you pay for insurance, plus the petrol that you use, but every now and then you need new tires. These are the points in time that you need new tires, and your car all of a sudden becomes a little bit more expensive to run, and then you forget about it, and then your tires are bald again. So that's the way that the cost develops for a manufacturing process of up to 5,000 devices with an aluminium mold. So when we're looking at thermoplastics, there's a advantage is that there's a wide range available, because one thing, COC, cyclic olefin copolymer, I think there's already 30 different grades in that one. So lots of different materials. We can combine materials. We can do something that's called overmolding. So we injection mold one material, and then we can add another material on top or around it. So we can do functional integration. We can combine different materials. Transparent materials are available, but COC is the only one that really goes deep UV. It is really cheap. We got a commercial sample of our COC, which was a bag about this high, and that was a free sample. People doing polymer processing really think large amounts, so 25 kilos is nothing. And it is compatible with high throughput manufacturing. The disadvantages is most polymers dissolve quite nicely in some organic solvents. So solvent compatibility may be problematic. Some are good, some are not, but it is always worth testing a corner of your device with the solvent you want to use to see if there's any, either it dissolves or it cracks. And so solvent compatibility may be a problem. Thermal resilience may be a problem. If you want to do PCR and you've got a thermoplastic that melts, where softening point is around 90 degrees, maybe not great. If you want to do organic synthesis at 180, some of your thermoplastics would work. The ones that, like COC is at around 220, that would be fine. PMMA is around 160, so you probably don't want to do PMMA. The surface chemistry is not as well known as glass. chemists have worked for decades with glass, they know what's happening. Plastics have not been in the lab so long. Unless you're talking about cell culture, because cell culture for years, decades has been done in polystyrene. So for cell culture, polystyrene would be fine. And the thermal conductivity of polymers is not as good as glass. So if you want to do fast thermal regulation, it will be still faster than in the bulk scale, but your thermal control in a quartz device would be a lot better than in a PMMA device. So these are all top-end technologies. The last 10 minutes or so of today, I'd like to show you that there's also different ways where you can make microfluidics just with something that you have available or you may be able to get from the hobby shop. We've got direct and indirect techniques where we can do micromilling. We then can do xerography, which is using a sharp laser blade to use an arm to cut little features out. There's 3D printing. There's also screen printing if you would like to make some functional electrodes. And in a space you can get a conductive ink and make your microfluidic devices by screen printing. With xerography, again, you can make stencils in different materials. And if you want to make functional materials like electrodes, you can also use photolithography to lift off all the metal that you've deposited other than in the area where your electrodes are. And that way you can use electrodes like here for dielectrophoresis. So photolithography comes in a whole range of different price classes. We've got the expensive one where we've got a mask aligner that has a mercury lamp in there and a chromium mask. But we can also do photolithography using an LED array as a UV source and a printed overhead transparency as a mask. So here we've got a setup made in a laboratory that wasn't very wealthy, where they've got a UV LED, some focusing and collimating optics, an Arduino microcontroller. You're all not engineers, but if we think back about the 3D printing lecture, we had the single board computer coming by. So an Arduino is a board that is around $10 to buy, and you can do your all programming. It's a single board computer, and it can control your instruments. So that's not a pound, that should be a rupee. So the Arduino microcontroller is cheap and allows to switch on and off the lamp and maybe have some feedback control on the light intensity. With the transparency mask, you get here, this is a 200 micron scale bar. You can see that with a simple transparency mask, you can actually get really nice templates being made up. And here they could get down to a 5 micron via using a UV LED and a transparency mask. So you don't necessarily need to have access to a clean room with a mask aligner and all the bells and whistles. A UV LED with a transparency mask can get you to really microfluidically very nice features as well. Micromilling is another way that you can directly make devices by having a quickly rotating spindle that can remove polymer. Here we've got the tip of the instrument. It looks a little bit like a drill, but other than a drill, we've got a very fine tip. And this fine tip can write microfluidic channels where the quality of the surface finish depends on how quickly the spindle moves. So at 5,000, you can see a few burrs on the sides. If we get this spindle to go really fast at 20,000 RPM, you can see that this microchannel here has got nice surfaces. And it is about 2.5 lakh to be able to mill your own devices in polymer. Again, not as exorbitant as the cost of a clean room. Laser ablation is another approach that you can use to make microchannels, where you hit your substrate with a laser and then your substrate is placed, or your laser is moved on an XY stage, and by changing the position of the laser on your PMMA plate, you can write your structures with the laser in the plastic. At the point that the laser light hits the plastic, there's so much heat being generated that all the polymer vaporizes and goes into the air, leaving a microchannel behind. Typically, these microchannels are going to be 500 micron and higher. But we found in my research group that if you put a 10 or 20 micron pinhole in front of the laser, you can actually narrow down this beam and make 20 micron channels simply by adding a small pinhole to a hobby laser writer that people use to make little arts and crafts things and decorations for birthday cakes. So here you can see some of the channels that we make with the laser cutter, where this is what happens without pinhole. And if you go with the pinhole, you can say that with a 50 micron pinhole and a 35 micron pinhole, we could get narrower and shallower microchannels. So here we've got a very big groove with a lot of material deposited on the sides. If we use the pinhole here, we can remove still material from the laser, but not as deep and not as wide. And even smaller pinhole, exactly the same happens. So if the problem is that our laser beam is too wide, we don't have to go and sit and cry in a corner. We can actually narrow it down using a very simple optical part. Xerography we've already seen coming by with the lady explaining the PDMS replication. They were using xerography to make their templates to cast PDMS. The desktop cutters are again not horrendously expensive. We can go to around 300 micron channels with desktop setup. One of the nice things is that once you make something with a laser cutter, you can go at half intensity, you can make little lines so that you can fold your device from, like origami, from a two-dimensional into a three-dimensional construct, so you can have different fluidic layers. So here, let's see if we can get the movie working. This is an explanation on how fast the xerography actually works. That is focusing a little bit more on the drawing of the designs. So that's the cutter. As you see, it's a small desktop instrument.
We'll cover the rapid prototyping of a microfluidic chip with two thin films of PET plastic and an inner layer of double-sided adhesive tape. We'll start by defining our chip design. Here I'm using a stand-in with 2 inlets and 3 outlets. You'll notice that there are 2 sketches here. They're both equal in size, the first of which we'll use to define our channel, the space in which fluid will flow through, and then the second one will define our inlets, our outlets, and the boundaries of our chip. I've mocked these up in Fusion 360, but you're free to use your favorite CAD package. This can be accomplished just as easily in COMSOL.
Or the free CAD package that we've seen last week.
Will be to save these files, or to export these files as images. In Fusion 360, this is done with a drawing exchange or DXF file. I'll save the first one, defining our channel.
So
and then do the same.
This goes a bit long, but it really shows you everything that you need doing, so it makes you also understand how quickly you can actually have a device.
Once we've done that, we can open the Cricut design space and start a new project. We'll click on Upload Image, and then in 2 steps, upload our channels and our through holes. Next, we can select these and insert them into our project space. There's several options at the top. One of the most important is the sizing. Here we'll define the width of the chip to be 1/2 inch, which scales to 1.5 inches lengthwise. Next, we'll select the channel here, click Attach to make sure that all of the cuts are done on top of one another, and then Make It. At this point, you can define where that chip is relative to the Cricut backing mat. Here I'll place it 8 inches along the x-axis and 1 inch along the y-axis before hitting Continue. At this point, you'll connect your material, to the Cricut, and when making the cuts for the channels, we'll select vinyl. The goal here is to thinly score the double-sided tape so that it can be peeled off later. Now we'll load the material into the Cricut and press Go. Here, those last few steps show.
See how fast this goes, so stay focused. Done. So it's now with this very sharp blade cut out this structure.
Once the Cricut has finished making its cuts, we'll reconnect, click Finish, remove the first sketch from our workspace, and then upload the one with the through holes.
So they are your reservoirs
The
that will
final
allow you
size,
later on to access the
54
fluidics.
is 1/2 inch in width, and ensure that it's rotated appropriately. Select this, click Attach to make sure that all the cuts are made on top of one another, and then click Make It. Once again, here's what those steps look like in real life.
Done.
Once the Cricut has finished making its cuts, remove the material and the backing board from the machine, turn the Cricut off, close the shell, and close out of the Cricut workspace before moving on to post-processing.
So that's important to make sure there's
First
no
step
dust
in
in there with your cutting
post-processing
blade.
is to remove the substrate from the backing. Your chip should then be able to pull apart really easily before moving on to the next step, where with a pair of tweezers or some other fine instrument, you'll carefully remove the tape lining the channel and punch out the inlet and outlet holes to your microfluidic chip. Then, adhesive side down, place your chip onto another PET film and press tightly to ensure a solid fit. As a quality control, here I applied about 10 microliters of blue dye to the chip, looking for any issues of seal or obstruction along the channel. This video is shown in real time, and as you can see, there was no evidence of either failure mode. This concludes this video of rapid prototyping of a microfluidic chip. Thank you.
So that shows that using a hobby laser cutter, a hobby cutter with a little blade, extractor machine, you can actually make microfluidic devices to try a couple of different designs yourself. And in this instance, they had one backing that wasn't patterned, one where the channels were removed from the middle, and one that contained the reservoirs to be able to get access to your channels. So very easy way of making the channels. I had planned to show this movie here during this lecture, but I already showed it this morning. So this is the Fluidigm quick way of making the microfluidic devices. Two different things that I'd like you to get out of this afternoon's lecture. One is scalability is important. The more closely you get to a commercial product, the more likely your gold standard will be your injection molder. But if you're starting off in the field of microfluidics, it may be worthwhile to look around what the tools are available in your department, or perhaps in the engineering department, that you could make work for you. Don't forget about the creative arts. There's a lot of these cutting machines and laser ablation that are used in the creative arts to make earrings. I'm pretty sure the earrings that I'm wearing at the moment are made with a laser cutter. They've got a little bit of the print laminated on. The shape, I'm pretty sure this was done by a laser cutter. One of our administrative persons in our department has purchased a laser cutter because she's making the decorations that you put onto a cake with Happy Birthday, Professor Malik. If you want to make that custom, laser cutters are the way that it's done. Local businesses. Our admin person has got a little business like that. There may be one here in Pachala that offers cutting polymers for very other purposes that you could use for microfluidics to make some simple fluidic structures as well. Think about laser engraving, micro milling. One of the tools that is really popular is Dremels, what people use to make jewelry. That is all very similar scale to microfluidics. And there is xerography, which is the one that we just saw the movie about, where a very sharp blade can cut to a fixed depth to remove parts of a polymer film, and you can then stick different parts of polymer together to use it as a spacer to leave a microchannel in the middle. The review article that's given here provides a very nice overview of the wide range of budget microfabrication technologies that have been used for microfluidics. So yes, replication by injection molding is great, but you need a machine that is this big, and your materials only come as a commercial sample from 25 kilos upwards. That may not be the good starting point for a career in microfluidics. There are a lot of machines that are used for very different applications that can be effectively be deployed for microfluidics. So that was replication. Tomorrow we go over even cheaper, and tomorrow we'll be looking at how you can use and pattern paper to do microfluidics on. And the second session we'll be moving to the chemistry department, where we're doing some hands-on fabrication of paper microfluidic devices. So thank you very much for your attention today, and now looking forward to seeing all of you again tomorrow.